Usually when we talk about like a medical diagnosis, there's this inherent expectation of precision. It feels almost like engineering.
Right. You want it to be clean.
Exactly. You break your arm, the x-ray shows that jagged white line, and the doctor just points at the illuminated film and says, there it is. That's the problem.
It's very binary. We inherently crave that level of visibility, broken or not broken, categorized.
But then you step into the world of, say, neurodevelopment or systemic autoimmune issues, and suddenly that x-ray machine is just useless.
Oh, completely.
We're looking at a diagnostic landscape that is incredibly murky. You're treating symptoms, you're guessing at underlying causes, and building these elaborate theories just to navigate the day-to-day reality of the patient. And today, we are taking that exact same lens, that intense friction between the clean structures we want to see and the really messy reality operating underneath, and applying it to the bleeding edge of artificial intelligence.
Because the absolute biggest obsession in the tech world right now, the multi-agent swarm, it might actually be a massive, really expensive illusion.
Welcome to the deep dive. We have a fascinating paradigm shift to think out loud about today.
We really do. And it truly is a paradigm shift. I mean, we are looking at the foundational architecture of how complex AI systems are being designed, funded, and deployed at scale.
Yeah. So our insights today, they come from a brilliant post by Rooted Layers AI Insights grounded on research. We're going to be referring to their work simply as the post throughout our conversation, but I really want to stress how rigorously researched this material is.
Yeah, the data they pull is incredible.
It is, because we are unpacking a massive paradox sitting right at the center of the industry. Everywhere you look right now, every startup pitch deck, every technical blog, they are universally talking about these societies of minds.
Right, the digital corporate office.
Exactly. The pitch goes like this, you don't just have an AI, you have a team, you spin up a CEO agent who outlines a strategy and talks to a coder agent. That coder agent writes a script, hands its work off to a reviewer agent. Maybe there's like a project manager agent chiming in to keep everyone on schedule. It sounds incredible.
It sounds great. It is a profoundly flattering story we tell ourselves about the technology. We anthropomorphize the code. We love the idea that we are engineering these distinct, specialized digital brains that collaborate just like a team of human experts around a boardroom table.
But the post suggests this entire architecture, this beautiful society of minds that everyone is rushing to build, might actually be a temporary workaround.
Yeah, not the final destination, but a structural stopgap.
Right. And for you, the listener, understanding why this is happening is critical, because whether you are actively building AI products or maybe allocating capital in this space, or just trying to understand the genuine trajectory of the technology, knowing the real bottlenecks of AI gives you a massive mental advantage.
It really does. Because if you understand why these multi-agent systems exist today and why they might fundamentally collapse back into single models tomorrow, you are miles ahead of the hype cycle.
Miles ahead.
If we connect this to the bigger picture, the people who win during major technological shifts, they aren't the ones who just blindly adopt the most popular framework of the month.
No.
They're the ones who understand the underlying physics of the technology. They know the mechanical reason a framework exists, which gives them the foresight to know exactly when that framework is going to become obsolete.
Okay, so I want to start by dismantling this society of minds narrative. Because it sounds so logical to a human, right? You want good code, so you hire a coder and a reviewer.
Makes perfect sense to us.
But the post argues this is just a flatteringly pretty description of a much simpler underlying failure. And to prove this, they highlight a benchmark study from a team at the University of British Columbia 2026. This team didn't just accept the multi-agent premise, they decided to aggressively stress test it.
They questioned the foundational assumption. The UBC team asked, is this complex graph of multiple conversational agents structurally necessary to achieve this output? Or are we just, making things complicated for the sake of it?
Right.
So they applied what they called a formal compilation function to an existing multi-agent setup.
Okay, let's break down what a compilation function actually means in this context, because they didn't just, delete the other agents. How do you take a CEO agent, a coder, and a reviewer and compile them into one thing?
Think about what those distinct agents actually are at a structural level. They're usually just the exact same underlying foundational model, say GPT-4 or Claude wrapped in different system prompts.
Okay.
The coder has a prompt saying, you write Python, and has access to a code execution tool. The reviewer has a prompt saying, you find bugs, and it has access to a reading tool.
So they're just wearing different hats.
Yep. Exactly. The UBC researchers essentially extracted all the specific tools and instructions from those distinct personas and compiled them into a single, unified library of skills. And they then gave that entire comprehensive library to one single agent.
They stripped away the costumes.
Yes.
Instead of 3 actors wearing different hats, they just gave one highly capable actor the entire script and all the props.
That is a highly accurate way to visualize it. And the performance metrics after doing this were just completely staggering. By collapsing the multi-agent system into one agent equipped with the compiled tools, token use dropped by 53.7%.
Wait, a 53.7% drop?
Yes.
For anyone managing cloud compute budgets, that is an absolute earthquake. I mean, you are essentially cutting your operational cost in half.
And that's just the financial cost.
Yeah.
Latency, the actual wall clock time it takes for the system to process the request and deliver the final answer, dropped by 49.5%.
So it's half the cost and twice as fast.
Exactly.
Yeah.
But the most critical data point from LI 2026 is that they achieve these dramatic efficiency gains while preserving comparable output quality. The single agent solved the problem just as well as the swarm did.
Okay, if the single agent does the exact same quality of work, but is exponentially cheaper and faster, the obvious question is why anyone is building multi-agent systems at all. It feels like a massive indictment of the whole trend.
It is a sobering result, but the Post is really careful to contextualize it. This doesn't mean multi-agent systems are entirely a scam, and it doesn't mean one single agent can handle every conceivable problem in the universe.
Right, there's nuance.
The implication is much narrower and vastly more useful for engineers. It suggests that for a significant portion of production applications right now, the explicit multi-agent structure is just the operational tax we are paying because our single models struggle with routing, state management, and internal coordination. We are compensating for the base model's current brittleness, not unlocking some magical new tier of cognitive capability.
A useful way to think about this is looking at early, hyper-inefficient corporate structures. Imagine a company where the internal communication is so broken that you end up with like 5 middle managers who spend their entire day drafting emails to each other.
Oh, I've worked there.
Right. Having alignment meetings, passing memos back and forth, just to produce one simple quarterly report. You don't actually need 5 middle managers to do the cognitive labor of writing the report. You just need one highly capable employee who has been given access to the right financial databases and a clear set of instructions.
Exactly.
The 5 managers aren't adding aggregate brain power. They're just a highly inefficient mechanism for organizing a workflow because the underlying system is fundamentally disorganized.
That analogy holds up perfectly under the scrutiny of the data. The multi-agent setup is often just a bunch of digital middle managers having verbose meetings in English, passing context windows back and forth, consuming millions of tokens, and adding massive latency to the system.
And the UBC study isn't an isolated finding, is it?
Not at all. The Post brings in another incredibly robust paper to back this up. It's called Towards a Science of Scaling Agent Systems by Kim et al. From 2025.
Oh, the 180 configurations study. Let's dig into the methodology here because the scale of what they tested is wild.
The rigor of the Kim paper is what makes it so undeniable. They didn't just test one specific coding task or one specific model. They systematically varied the variables. They controlled for the raw quantity of agents. The topology, meaning how the agents were structurally connected to each other, like a chain, a hierarchy, or a flat debate panel.
Okay.
They controlled for the underlying capability of the base model and the complexity of the task itself. And they ran this across 180 distinct configurations.
So if the industry narrative was true, that more agents collaborating intrinsically creates more intelligence, you would expect a relatively clean upward-sloping graph, right? Like, as the agent count goes up, the success rate goes up.
The graph did not slope upward. The headline finding of the Kim paper is that outcomes are heavily constrained by a brutal trade-off. It's a trade-off between the overhead of tool coordination, the inherent saturation point of the base model's reasoning, and the amplification of errors within the system's topology.
Wait, the amplification of errors?
Yeah. Under fixed computational budgets, a few multi-agent variants showed marginal help on highly specific parallel tasks. But across the full spectrum of the 180 configurations, the mean improvement of adding more agents was literally negative.
Meaning that, on average, taking a task and assigning it to a swarm of agents actively made the system perform worse than just giving it to a single model.
Yes.
Let's unpack the mechanics of why it gets worse. What is physically happening in the system that degrades the output?
Well, every time an agent hands off a task to another agent, you introduce a point of failure. The first agent has to summarize its findings into text. That summarization is inherently lossy. It drops
Like
nuance.
a bad game of telephone.
It's exactly like telephone. The second agent then reads that text and has to interpret it. If the first agent hallucinates a minor detail or formats a variable incorrectly, the second agent takes that error as absolute truth and builds upon it.
Wow.
In a chain of 5 agents, a tiny hallucination at step 1 compounds into a catastrophic failure by step 5. You are spending your computational budget on coordination of overhead and error propagation rather than indispensable reasoning.
Which brings up an interesting pivot. If a single agent is significantly faster, cheaper, and less prone to compounding handoff errors, why did builders ever move away from them? I mean, no engineer wakes up and decides to build a massively inefficient, lossy system on purpose.
Right.
There had to be a technical wall they hit with the single agent that forced them to invent the swarm in the first place.
You are identifying the exact friction point that drives the entire architecture of modern AI. And it leads us directly into what the Post categorizes as the disambiguation threshold. Single agents are magnificent, but they have a breaking point. Eventually, that one highly capable employee gets completely overwhelmed by the sheer volume of tools you pile on their desk.
Okay, let's explore this collapse zone. When exactly do single agents break down?
To find the boundary, the UBC team kept pushing the single agent. They didn't just prove it was cheaper, they methodically added more and more tools to the single agent's compiled library to see when it would fail. And they observed that skill selection by a single model does not degrade gracefully.
It doesn't slowly get worse.
No, it stays remarkably stable, maintaining high accuracy, and then it suddenly falls off an absolute cliff.
Like hitting a cognitive brick wall. So where is the wall?
On the models they tested, that catastrophic collapse zone happened right around 80 to 90 skills.
Wait, so if I give my single AI agent a library of 50 tools, let's say it can search the web, calculate math, read PDFs, access a weather API, and query a database, it handles it perfectly. It knows exactly which tool to pick for which user prompt.
Yes, perfectly fine.
But the moment I expand that library to 85 or 90 tools, it suddenly just loses its mind and starts picking at random.
The breakdown is severe, and it's driven by a highly specific mathematical problem called semantic confusibility.
Okay, we need to pause and really pull the mechanics out of that term. Semantic confusibility sounds fascinating. What is actually happening inside the model's neural network to cause this?
Well, we have to step away from how humans perceive language and look at how a machine learning model perceives language. A model doesn't inherently know what a tool does in the physical world. It doesn't have a human understanding of a database.
Right.
It only has the text description of the tool that the developer provided. And the model maps these text descriptions into a high-dimensional mathematical space using semantic vectors.
Okay, let's give the listener a mental image of that. Imagine a massive physical space, like an infinitely large room. Every single word and concept gets assigned a specific coordinate in that room based on its meaning. Words that mean similar things are physically placed closer together in this mathematical room.
That's a great visualization. Now, imagine you have a massive library of 90 different business tools. Inevitably, the descriptions of some of those tools are going to map to coordinates that are incredibly close together in that room. For example, let's say you give an agent a tool called Resolve Customer Ticket and another tool called Refund or Payment.
To a human customer service rep, those are night and day. Resolving a ticket just means closing out the chat window because the customer said thank you. Refunding a payment involves interfacing with the banking system and moving actual currency.
But look at the text descriptions you would write for those tools. Both descriptions will likely contain words like customer, satisfaction, order issue, user ID, and resolution.
Ah, I see.
In that high-dimensional mathematical room we just visualized, the semantic vectors for those two tools are sitting right next to each other. They are mathematically blurred. So when a user prompt comes in asking to fix an order, the model's internal selector logic tries to find the right coordinate. But because the target area is so crowded with similar tools, the selector essentially collides with itself.
It just can't distinguish them.
Exactly. The UBC setup found that injecting even just one semantically similar competitor tool into the library can materially destroy the model's accuracy in selecting the right action.
Wait, this reframes everything. When a developer creates a distinct database expert agent and a distinct marketing copywriter agent, they aren't actually conjuring up new specialized virtual brains.
No.
They are just building fences. They are building a fence around a specific set of database tools so the AI doesn't accidentally wander over and use the marketing tools because the semantic vectors were too close.
You've just articulated the core foundational insight of the entire post. This fits a broader pattern we're seeing in software engineering, where isolation is used strictly to manage complexity.
Yeah.
In a vast majority of production systems today, developers aren't creating a specialized persona because the task demands a mystical new type of intelligence. They are creating it because throwing query your database, fetch marketing campaign metrics, and check user entitlement into one giant flat list of tools causes catastrophic routing confusion.
Wow.
The agent boundary exists purely to keep similar actions mathematically separated.
The agent is just a namespace. For anyone who has written code, you know what a namespace is. It's just an organizational folder. You put all your database functions in the database folder and your customer service functions in the customer service folder, just so the program doesn't get confused and try to execute a refund when it's supposed to be writing a SQL query. The agents are just folders.
The post states it explicitly. They say, this is the point where agent stops meaning persona and starts meaning namespace. It strips away the romanticism of the society of minds, but it fits the empirical engineering data vastly better. And more importantly, this interpretation mechanically explains why hierarchical routing works so effectively as a solution to this problem.
Let's explore hierarchical routing. How does creating a hierarchy bypass this semantic confusibility problem we just talked about?
Well, let's go back to the UBC experiments. Making a flat, single-shot selection from a massive library of 90 tools fails because the mathematical space is too crowded. Hierarchical routing fixes this by replacing one massive overloaded decision with a series of smaller, highly distinct decisions.
Okay.
Instead of asking the model to pick one tool out of 90, the system first asks a higher-level routing model. Is this user request a database problem, a customer service problem, or a marketing problem?
And the semantic vectors for database and marketing are miles apart in that mathematical room. It's a wildly easy distinction for the model to make.
Precisely. Once the router successfully makes that easy choice and selects database, it routes the request to a subagent. But that subagent doesn't have 90 tools. It only has the 10 specific database tools. The crowding is gone.
I love this because the model didn't magically get smarter. You just altered the architecture of the test. You took a terrifying multiple-choice test with 90 similar options, and you turned it into a simple decision tree where every branch only has 3 obvious choices.
And the post highlights 2 specific architectural solutions currently leading the literature on this. The first is a 2026 paper by Al-Zubi et al., introducing an architecture called Roma. It leans heavily into this recursive structure, defining 4 explicit modules. There's an atomizer, a planner, an executor, and an aggregator.
That sounds heavy. Atomizer, planner, executor, aggregator. Walk me through how a request actually flows through that pipeline. Let's say I ask the system to analyze my company's quarterly sales and generate a forecast.
The key to Roma is that it aggressively manages the local context. The atomizer receives your massive request and immediately breaks it down into isolated subtasks. It separates fetch Q1 data from calculate growth trends.
Okay.
The planner then takes a single subtask and maps out the necessary tool calls. The executor runs the tools, the aggregator collects the output. But here's the critical mechanism. The aggregator compresses the intermediate outputs before passing them back up the chain.
Ah.
It refuses to hand the next step a bloated, raw transcript of everything the executor just did. It hands over a tightly compressed summary.
Which directly attacks the issue Kim et al. Found with 180 configurations, the compounding error of passing massive context windows around. By forcing compression at the aggregator stage, you prevent the model from drowning in its own bloated logs.
That's exactly the mechanism at play, and the benchmarks prove it out. On complex reasoning datasets like SEAL0, this specific Roma design produced a measurable 9.9% improvement over flat models. The takeaway here isn't that this specific recursive loop is the ultimate answer to everything. The takeaway is that once your action space crosses the disambiguation threshold, once you have too many tools, rigorous structural decomposition of the problem is exponentially more valuable than just writing a louder, more aggressive system prompt.
Stop yelling at the model to think step by step and start physically breaking the steps apart for it.
Yes. Exactly. Now, the second solution the post mentions addresses the routing problem from a different angle. It's a 2026 paper by Wang et al. Called Skill Orchestra.
Skill Orchestra?
Yeah. Instead of relying on an opaque routing policy where a model just guesses which persona should handle a task, Skill Orchestra forces the system to build and maintain a reusable skill handbook.
Handbook, like an internal resume for what the different parts of the system are actually capable of.
Yes, but highly quantified. It actively profiles the competence of different agents and tracks the computational cost of invoking specific tools. When a request comes in, it routes the task based on explicit mathematical performance cost trade-offs rather than relying on a vague semantic match of a persona description.
That is a massive paradigm shift. Instead of a prompt saying, you are a world-class senior software engineer, the system looks at a handbook that says, Agent 4 has a 92% success rate with Python scripts under 50 lines. It costs 0.04 cents per execution, and its historical error rate on loop structures is 3%. And the orchestration layer makes a routing decision based on hard historical telemetry.
Orchestration becomes defensible. It is tied to explicit capability profiling. As the post points out, this is exactly where practical agent stacks need to mature. If you are building a multi-agent environment primarily to prevent tool confusion, you have to admit that to yourself. It's not a failure. It's a profound clarity of purpose.
Because once you admit that your swarm is just a complex router, you can start agonizing over fake persona prompts and start building actual engineering solutions. You can step back and ask, do I really need a multi-agent swarm here, or do I just need smaller tool libraries? Do I need a cost-aware routing handbook like Skill Orchestra? The amateur conversation is, we built a massive swarm of 20 agents because the problem was incredibly complex. The senior engineering conversation is, we needed to lower the semantic ambiguity per decision, so we cleanly partitioned the action space.
It fundamentally changes how you architect the system from day one.
Okay, I want to push back on this a little bit, or at least pivot our perspective. We have spent the first half of this deep dive absolutely tearing down the multi-agent swarm. We've called it an illusion, a workaround, a namespace born from semantic confusibility. But the post is clear, and intellectual honesty demands we acknowledge this. Multi-agent systems are not entirely fake.
They are absolutely not fake in all contexts. A rigorous architectural argument has to address the exceptions directly. The post identifies 4 specific structural domains where multi-agent systems are genuinely load-bearing.
Meaning,
in these 4 scenarios, the separation isn't a workaround for routing confusion. It is a fundamental requirement of the physics of the task.
let's dissect these 4 domains. If I'm an engineer and I've simplified my routing, I've kept my tool library small, and I've implemented a handbook, when do I still undeniably need multiple distinct agents? What is the first scenario?
The first domain is heterogeneity. This is when your system genuinely requires different underlying substrates to function.
Unpack the word substrates for me in this context.
Yeah.
What makes 2 models heterogeneous?
Well, we have this habit in the industry of pretending that a massive text-based language model is a universal sponge. We throw a spreadsheet at it, we throw a photograph at it, we throw complex spatial logic at it, and we just expect the transformer architecture to process all of it perfectly.
Right, the omnipotent chatbot.
But the reality of machine learning is that different modalities often require fundamentally different mathematical architectures. A vision model utilizes convolutional layers or vision transformers that are deeply optimized to process raw arrays of pixels and understand spatial relationships. A text model is optimized for sequential token prediction. A formal logic verifier operates on deterministic symbolic math.
So in this scenario, multiple agents are not just one single underlying model wearing different prompt hats. They are physically different types of digital brains.
Yeah.
They are trained on entirely different data sets, using entirely different loss functions, operating on different physical principles.
Exactly. The post details a fascinating 2026 paper called The Vision Wormhole by X. Liu et al., which takes this heterogeneous reality very seriously. It proves empirically that when the required capabilities differ materially, you cannot just force them all into a homogeneous text model without suffering massive performance degradation.
You just lose fidelity.
Yeah. You need the specialized vision architecture to look at the image and the specialized text architecture to write the report. The separation between them isn't a workaround. The separation is the entire value of the system.
A useful way to think about this is software tooling. You technically could represent every single pixel of a high-definition video as a colored cell in Microsoft Excel and try to edit a movie by writing macros to change the cell color.
Oh, that sounds like a nightmare.
Right. It is technically possible, but it would be a catastrophic nightmare. You need Adobe Premiere for video, and you need Excel for spreadsheets. They are different substrates. Okay, what is the second domain where swarms are mandatory?
The second domain revolves around trust and authority boundaries.
Oh, this is critical. We are moving from capability to governance.
The post references a 2026 paper called Intelligent AI Delegation by Tomashev et al. The post explicitly notes this is more of a conceptual framework than a pure benchmarking paper, but it identifies a non-negotiable requirement for production AI. Sometimes you separate agents entirely for safety.
Give me a concrete scenario of how a trust boundary operates in an AI system.
Imagine you have an AI system deployed at a hospital, responsible for analyzing patient data and recommending complex medication dosages.
Okay.
You absolutely must have a secondary system acting as a safety critic, an agent whose sole purpose is to aggressively interrogate the proposed dosage against a database of known drug interactions and patient allergies before it is shown to a human doctor.
And you can't just have one model do both. Why can't the model just generate the dosage and then critique its own work in the next sentence?
Because of the risk of weight contamination.
Yeah.
If the generator and the critic are just the exact same neural network being prompted differently, they share the exact same internal latent space. The model might subtly align its critic persona with its generator persona to avoid conflict, or it might hallucinate a highly convincing, totally fabricated medical justification to defend its own initial error.
It's grading its own homework, and it knows exactly what lies to tell itself to get an A. Let's take that analogy a step further into corporate accounting. You do not merge the employee who spends the corporate budget and the internal auditor who reviews the expenses into one single role just to save on payroll costs.
You'd go to jail.
Exactly. The friction between those two roles is the entire point. The separation is a feature, not a bug. If the spender is the auditor, you are mathematically guaranteeing fraud. You need structural, physical isolation.
That is the exact principle. You need a safety verifier that is physically isolated, perhaps even running on entirely different hardware, governed by an entirely different set of alignment protocols. You cannot fold those boundaries away into a single agent without completely erasing the governance structure that makes the system safe to deploy in the real world.
Okay, heterogeneity and trust boundaries. What is the third domain?
Embodied or distributed coordination. This applies when agents have to exist and operate within a shared physical or digital environment simultaneously.
So we're talking about robotics, autonomous vehicles, or agents inhabiting a shared simulation.
Exactly. The post highlights two important papers here. MCOOP by H. Yang et al., 2026, and Multi-Agent Bench by Zhu et al., 2025. When agents share an environment, they're subjected to the chaos of physics and time. They interrupt each other, they physically block each other's paths. One agent drops a tool that the other agent needed.
It's messy.
They are forced to replan their actions in real time based strictly on the unpredictable actions of the other agents in the space.
It fundamentally breaks the clean, turn-based logic of a server. Routing an API call in a text-only workflow is a pristine, isolated event. Coordinating two robotic arms that are trying to weld a car chassis together without smashing into each other is a dynamic, continuous negotiation.
That's why the multi-agent bench paper is so vital. It shifts the evaluation. It treats the coordination protocols themselves, how the agents negotiate space, time, and shared resources, as the primary evaluation metrics, not just an afterthought to task completion. When multiple autonomous actors must coordinate in a shared state, the system-level interaction between them is genuinely irreducible. You cannot compile two distinct autonomous drones into one super drone without fundamentally altering the physical reality of the task they are performing.
Which brings us to the fourth and final domain, where multi-agent swarms are genuinely load-bearing. Heterogeneity, trust, embodied coordination, and what is the last one?
Exploration.
Exploration, as in searching a vast space for a novel answer.
Yes. The post cites a 2026 paper called EMPO2 by Zilue et al. Sometimes, the primary objective of your system isn't to find a good enough answer quickly, and it isn't to minimize latency. Sometimes the objective is to maximize the surface area of your search across a massive, highly complex space of possible solutions.
Like an AI trying to discover a novel protein folding structure or trying to crack an incredibly dense cryptography problem, you do not want one single agent making one linear guess. You want a massive swarm of agents taking wildly different, highly divergent, parallel approaches to the problem simultaneously.
Exactly. Launching multiple actors to generate independent, contrasting trajectories of thought is completely rational and necessary here. Even if you eventually take all those thousands of different discoveries and distill them down into one final report, the physical act of searching required the parallel power of the swarm. The scaling paper we discussed earlier, Dash et al., confirms this. Their data show that while sequential reasoning tasks degrade with more agents, centralized coordination of highly parallelizable search tasks can actually see massive benefits from a swarm structure.
So multi-agent isn't magic, and it isn't the default answer. It is a highly specific, conditional tool that is deeply necessary for four distinct physical realities: processing different hardware substrates, enforcing safety audits, negotiating shared environments, and executing massive parallel search.
Precisely. But arriving at this realization, accepting that multi-agent systems must exist in these specific domains, forces the industry to confront a massive, glaring architectural flaw in how we are currently building them.
Which brings us to a critical pivot in our deep dive: the death of English. Or more broadly, communication as the next major frontier in AI architecture. If we accept that some systems absolutely must have multiple distinct agents, how on earth are they supposed to talk to each other? Right now, they talk to each other almost entirely in natural language. They write English paragraphs. And the Post argues that this is a catastrophic structural bottleneck. Let's unpack the mechanics of why text is so bad. Having two incredibly advanced AI models talk to each other in plain English seems incredibly intuitive to us.
It is intuitive to us because English is our native latent space. It is the highest bandwidth communication protocol the human brain possesses. But for a massive machine learning model, translating its rich internal logic into a sequence of English words is aggressively inefficient. Consider the mechanics of a handoff. Model A has just spent 20 seconds processing a complex problem. Its internal state, its understanding of the problem, is represented as a massive matrix of high-dimensional math. Millions of floating point numbers capturing probabilities, context, and structural relationships.
Okay.
To pass that insight to Model B, it is forced to compress all of that rich, multi-dimensional math down into a linear one-dimensional sequence of English text.
It is forced to write a summary. And anytime you summarize something complex, you drop nuance.
It is extreme lossy compression. Model A loses a massive amount of its subtle mathematical context. Then, it sends that text string over to Model B. Model B receives the text and has to mathematically reconstruct the entire meaning from scratch, guessing at the context that Model A was forced to leave out of the summary. It's a slow, bandwidth-starved process that introduces massive hallucination risks right at the translation layer.
A useful analogy here is trying to send a high-definition IMAX movie to your friend, but your internet is down. So instead of sending the video file, you sit down and write a highly detailed 50-page text summary of every single shot, every lighting change, and every line of dialogue in the movie. You hand your friend the text, and they try to mentally recreate the IMAX experience in their head based solely on your words. It takes forever, and the movie they picture in their head is going to be wildly different from the actual film. That is what AI agents are doing to each other right now.
That is a brilliant visualization of the lossy compression problem. And the field is realizing this cannot continue, which is why the Vision Wormhole paper is so revolutionary. They proposed a truly alien solution to this problem. They realized that the visual pathway, the architecture inside vision language models designed to process images, could be repurposed as a massive, high-bandwidth communication channel.
Wait, I need to make sure I understand the mechanics of this. They forced the models to communicate by sending images to each other instead of text.
Conceptually, yes. They bypassed the narrow text bottleneck entirely. Think of text processing as a very narrow straw, constrained by sequential tokens. The visual processing pathway, however, is designed mathematically to ingest and process massive arrays of millions of pixels simultaneously. It is a giant fiber optic cable. The researchers found a way to take the dense, intermediate mathematical representations from the first model and pipe them directly through the wide visual pathway of the second model.
They hijacked the model's optic nerve to transmit raw data matrices. That is one of the most wildly creative hacks I have ever heard. What did the data show? Did it actually improve the system?
It worked brilliantly. On their tested heterogeneous setups, moving away from text and using this visual pipeline produced an average accuracy gain of 6.3 percentage points, and the entire system executed roughly 1.87 times faster.
It almost doubled the speed of the system just by skipping the English translation step.
And this push away from text is happening across multiple vectors of research. The Post also highlights a 2025 paper called Latent Collaboration in Multi-Agent Systems by Zhu et al. They introduced a framework called Latent MAS, which is completely training-free. Instead of translating the handoff to text or even using a visual pipeline, they literally extract the hidden state information, the raw internal mathematical activations firing inside the layers of the first model, and inject them directly into the layers of the second model.
Okay, wait. If it's moving raw neural activations directly from one brain to another, it's essentially telepathy. The first model is just dumping its raw brain state into the second model. It's skipping the mouth and the ears entirely. But I have to push back heavily here. If we build systems where agents are communicating via latent hidden states or visual wormholes or raw matrices of floating point numbers, don't we completely lose our ability to read the logs? How do we audit a system if we literally cannot comprehend the language it is speaking to itself? If the safety critic from our hospital example is talking to the dosage generator in pure latent math, how does a human doctor step in, review the logs, and ask, why did you approve this lethal dose?
You are hitting on the exact central tension of this new architectural frontier, the friction between efficiency and observability. The Post does not claim this is a solved issue. It is a massive trade-off. If you are operating in a highly regulated environment like healthcare or finance, where a human-readable audit trail is legally mandated, you might be forced to keep the English text layer. You will have to accept that your system is going to be 50% slower and significantly more prone to translation errors, simply because you need to be able to read the transcript.
So you have to choose fast, highly accurate, and completely alien to humans, or slow, error-prone, but fully readable.
Exactly. But regardless of which side of that trade-off a builder lands on, the research is crystal clear on one thing. The MCOOP paper provides a stark warning about our current default behavior. MCOOP found that when you allow agents to engage in unstructured high-volume text chatter, just endlessly debating each other in verbose English paragraphs, it actually destroys planned coherence. The system gets lost in its own noise. It massively increases decision overhead and degrades the actual intelligence of the final output.
It's like a massive corporate Slack channel where 60 people are talking over each other in huge multi-paragraph rants. Nothing actually gets decided, the core plan is buried, and the system grinds to a halt.
That is exactly what happens mathematically. So the immediate actionable takeaway for engineers isn't necessarily, you must invent a latent math telepathy protocol tomorrow. The takeaway is much more grounded. Stop treating verbose English handoffs as a free, harmless abstraction. They're computationally expensive, slow, and actively destructive to coherence. If your agents absolutely must communicate in text for auditing reasons, you must force them to exchange the absolute smallest, most rigorously structured state possible.
The Post has a brilliant phrasing for this. It says, prefer typed fields over paragraphs, prefer compact plans over autobiographies, prefer bounded schemas over self-important debates. I love the idea of stopping an AI from writing a dramatic autobiography every time it just needs to hand off a single integer variable.
It requires extreme discipline in system design. The frontier of research might be pushing toward raw, latent communication, but the immediate practical victory for anyone building a system today is enforcing strict, minimalist, structured chatter.
Okay, let's zoom out and look at the macro trajectory of everything we've discussed. We've established that multi-agent systems are frequently just workarounds for routing failures. We know exactly where the disambiguation threshold sits. We've identified the 4 specific domains where swarms are physically required. And we know that their communication architecture must rapidly evolve away from verbose English. If we take all of these massive trends and project them forward, what is the ultimate destiny of today's sprawling multi-agent swarms?
This brings us to what might be the most profound, counterintuitive insight in the entire Post. We have to view the swarm not as a final product, but as a phase in a life cycle. If single foundational models are constantly getting better at managing internal tools, and if multi-agent systems are heavily reliant on external scaffolding to function, the logical conclusion is that today's massive multi-agent swarm is actually just tomorrow's training data.
Wait, I need you to explain that. The swarm itself is the training data.
Yes. The core pattern emerging in the bleeding-edge literature is that the incredible reasoning benefits generated by a complex multi-agent system can actually be distilled and used to improve the base policy of a single model. You do not build the massive swarm to run in production forever. You build the swarm in the lab to teach a single model how to think properly.
Let's try to visualize this. A useful way to think about this is putting training wheels on a bicycle. The multi-agent swarm is the set of training wheels. You bolt on all of these external helpers, you add a distinct planner agent, a reviewer agent to check the work, a memory agent to keep track of the context, and you use all of this heavy external scaffolding to help the core system learn the complex balance of generating multiple trajectories, verifying its own logic, and correcting its mistakes without falling over. But you do not leave the training wheels on when you enter the Tour de France. Once the core system has fully internalized the mechanics of balance, you strip all the scaffolding off, and you run the single, sleek, highly capable model in the actual race.
That analogy captures the exact mechanical life cycle the industry is moving toward. You cannot view AI architecture as a static, permanent schematic. You have to view it dynamically. And the post cites 3 major recent papers that prove this training wheels internalization pattern is already yielding massive results.
Let's dive into the mechanics of these papers. What is the first one showing us?
The first is EMPO2 from Zilu et al., 2026. This paper focuses heavily on the training phase. In their setup, during training, the agent is provided with external memory tips. This is the scaffolding. These tips help the agent explore the vast problem space more efficiently and find high-quality solutions. But the magic happens during the off-policy updates.
Okay, we need to pause and define off-policy updates mechanically. What is the model actually doing to its internal math during an update?
In reinforcement learning, a model tries actions in an environment to maximize a reward. On-policy means the model is learning strictly from the actions it is currently taking based on its current rules. Off-policy means the model can learn from data or trajectories generated by other policies or past experiences. In the EMPO2 setup, the model generates a great trajectory using the external hints. But when it goes to update its internal neural weights, adjusting the math so it is more likely to take those good actions in the future, it recomputes the probabilities without relying on the hints.
It uses the hint to find the right answer, but it forces itself to learn the pathway to that answer so deeply that it won't need the hint next time. It burns the lesson into its base weights.
Exactly. The base policy physically internalizes the useful behavior. And when they tested this on complex benchmarks like Science World and WebShop, this hybrid approach of using external scaffolds to generate data and then internalizing the lesson materially outperformed baseline models. The profound lesson here isn't that we have perfectly solved external memory. The lesson is that external scaffolding is incredibly valuable precisely because it produces high-quality reasoning trajectories that are worth internalizing into a single base model.
It's an automated teacher generating perfect examples,
Yeah.
and the student model learns from those examples until the teacher isn't needed. That makes total sense. What is the second paper?
Agentic Memory by Yu et al., 2026. This paper tackles state management. Look at almost any complex enterprise AI stack today. You will almost always find a dedicated, separate memory agent. Its entire existence is dedicated to sitting to the side, reading the ongoing context, and deciding what information needs to be saved to a vector database and what information can be deleted to free up space.
Right, because if you don't aggressively manage the memory, the main model will just bloat its context window until it crashes or starts hallucinating wildly. You hire a digital maid to clean the room.
Precisely. But agentic memory proves that the digital maid is temporary. Instead of building a separate controller agent, this architecture exposes all the memory operations store, retrieve, update, summarize, filter, delete as internal native tool actions directly within the single base policy. It mathematically trains the single agent to govern its own memory state.
You train the single agent to clean its own room, and mechanically it just learns when to fire the delete tool based on its own internal state rather than relying on an external observer.
Exactly. And the benchmark results show that this unified internalized memory policy significantly improved both performance and context efficiency over strong baseline models that used external memory agents. The post is adamant about this. If your current architecture mandates a separate memory agent, it is solely because your base agent has not yet been adequately trained to govern its own memory. Once it receives that training, the agentic boundary completely disappears.
Which brings us to the third paper. And based on what we've just discussed, this one sounds like the definitive end of the permanent multi-agent swarm. Let's talk about Tark.
Tark by Luber et al., 2026. This paper provides the most direct empirical evidence for the swarm as training data thesis. The researchers successfully utilized process-aware distillation to transfer multi-agent reasoning traces back into a single model, massively improving that single model's performance.
Okay, process-aware distillation. Let's break down the mechanics of how you distill a conversation into a model weight. They literally ran a multi-agent swarm, recorded the agents debating, checking each other's work, and correcting errors, and then fed those raw transcripts into a single model.
That is the essence of it. Standard distillation usually just takes the final, correct answer from a massive model and trains a smaller model to produce that same answer. But process-aware distillation captures the entire journey. It captures the initial hypothesis, the critique from the reviewer agent, the correction the tool calls. It takes that entire rich, multi-agent reasoning process and uses it as the target training data for the single model. The single model learns to replicate the entire internal debate natively. Now, the post exercises appropriate caution here. It notes that this doesn't guarantee that every single ounce of multi-agent intelligence can be transferred with zero loss, but it strongly, undeniably supports the macro pattern. A complex swarm is a highly effective training rig.
This realization completely upends how an engineering team should think about product development. You do not build a massive 15-agent swarm with the intention of deploying it live to millions of users. That would be a catastrophic waste of compute, time, and money. Instead, you build that complex swarm strictly in your R&D lab. You let the agents debate, you let them struggle with routing tools, you let them aggressively correct each other, and you meticulously log every single high-quality decision tree they produce. Then, you take those logs, run a process-aware distillation, and train a single highly optimized foundational model to execute all of that complex reasoning internally.
You systematically strip away the incredibly expensive high-latency inference time ceremony. This is what the post beautifully terms a healthier engineering loop. You prototype with heavy, multi-agent scaffolds to find the bounds of the problem. You log the successful trajectories, you internalize everything you possibly can into the base model's weights. And you only retain external multi-agent scaffolding in production when it is genuinely physically load-bearing, like the absolute trust boundaries or heterogeneous substrate requirements we broke down earlier.
Okay, this has been an incredibly dense, profound journey through the absolute bleeding edge of AI architecture. We have covered massive amounts of theory, benchmarking data, and complex mechanics. But the entire purpose of this deep dive is to give you, the listener, an immediate mental advantage. So let's land this plane. The post concludes by synthesizing all of this research into an actionable builder's playbook, alongside 2 highly specific predictions for 2027. Let's walk through this playbook as a cohesive design philosophy. If an engineering team is sitting down to architect a new AI system tomorrow morning, how should this research change their behavior?
The post outlines a progression that fundamentally demands restraint. The very first principle is, start with a single agent, just one model equipped with a library of tools. Do not proactively introduce distinct personas, multiple agents, or complex routing topologies until you can mathematically identify the exact bottleneck you are failing to cross. You have to earn your complexity.
Prove that the single model is failing before you build the corporate office. And when it does fail, when you hit that disambiguation threshold around 80 tools, you don't immediately jump to a 20-agent debate panel.
Exactly. When the routing collapses, you move to the second principle. Think in namespaces and localized action spaces. Use recursive structures like the Roma architecture we discussed to strictly manage the local context. Do not try to solve tool confusion by writing a louder, more aggressive system prompt. You cannot yell a model into being smarter. You have to structurally decompose the decision so that every single choice the model faces is drastically below its semantic confusion threshold.
Make the choices smaller and clearer. And if you absolutely must split the system into multiple distinct entities, the playbook warns against flat committees.
Yes, avoid flat, unstructured debate panels at all costs. If you need multiple agents, use explicit, skill-aware routing. Implement something like the Skill Orchestra Handbook, where routing decisions are made based on hard telemetry cost, latency, and historical error rates, rather than relying on the vague semantic vibes of a persona description.
And once that structure is in place, you have to ruthlessly govern how the pieces talk to each other.
This is the communication imperative. Minimize natural language handoffs immediately. Stop the verbose autobiographies. Force your agents to communicate via typed fields and bounded schemas. And as the technology matures, begin experimenting with rich, latent internal channels, but only deploy them when the immense computational cost is definitively justified by the task.
Which requires aggressive observability. You have to measure the friction of the process, not just the final outcome. If you are blind to the communication load or the compounding error rates during handoffs, you don't actually know why your system is succeeding, and you'll be completely lost when it fails.
And the final principle is the ultimate lifecycle view we just explored. Treat all external scaffolds, memory agents, review passes, debate panels as prime candidates for internalization. View them as temporary training wheels that belong strictly in your offline adaptation pipelines, not in the hot, expensive path of every single live production request.
It is an incredibly crisp, grounded design philosophy. A deeply skeptical engineer could summarize the entire paradigm shift in one sentence. Multi-agent systems generate immense value through specific coordination mechanisms, but almost all of those mechanisms can ultimately be simplified, compressed, or completely internalized into a single base model once you truly understand the mathematical problem you were trying to solve.
That is the perfect distillation of the post. And to prove how inevitable this trajectory is, the author finishes with 2 highly specific, completely falsifiable predictions, staking a claim on the exact state of the industry by the end of Q1, March 31st, 2027.
I deeply respect a falsifiable prediction. Put a hard date on the calendar and let the market prove you right or wrong. What is the first prediction for March 2027?
Prediction 1. By March 31st, 2027, at least one major agent framework or major hosted platform will ship built-in graph simplification or automatic evaluator tooling. This means the platform itself will analyze your sprawling 15-agent workflow and automatically recommend compiling parts of it back into a single agent setup to save you compute.
That is brilliant. The tools we use to build the swarms will actually start actively fighting against swarm bloat. They will say, hey, I analyze your telemetry, and these 4 agents are just wasting tokens. I can compile them down into one agent and save you 40% on latency. It is the exact same evolution we saw in traditional software compiling. Early programmers wrote highly inefficient code, and eventually the compiler got smart enough to automatically optimize away the human inefficiency and pack it into tight machine logic.
Precisely. If by 2027 the major frameworks are still solely focused on helping you build increasingly massive multi-agent graphs without offering a first-class automated simplification pass, the prediction fails. But given the brutal economic pressures on inference costs right now, it is overwhelmingly likely to occur.
And what is the second prediction for 2027?
Prediction 2. By March 31st, 2027, at least 2 publicly detailed production-grade compound AI systems from major Tier 1 vendors will explicitly utilize non-text intermediate handoffs for their internal coordination.
The death of English inside the machine becomes a production reality.
Yes. Whether they achieve it through highly typed model-native state transfers or pure latent visual pathways like the Vision Wormhole, the text bottleneck will be bypassed. If the massive tech labs are still relying exclusively on natural language paragraphs or clunky JSON relay scripts for their internal multi-model coordination by 2027, this prediction is false.
But based on the massive latency and lossy compression issues we unpacked today, they are absolutely going to find a way to pipe the high-dimensional math directly. The frontier of this technology is not simply how many agents can we wire together. The true frontier is optimizing state movement, managing semantic boundaries, and knowing exactly the right moment to fold the entire complex system back into one unified, elegant model.
The conversation in the field is rapidly maturing. We are moving from the theatrical hype of societies of mind to the rigorous physics of finding the absolute most efficient thermodynamic path for computation.
Let's synthesize the massive journey we've been on today. We started by looking at this incredibly comforting, deeply human illusion we've constructed, the digital corporate office, the society of minds. And by looking at the hard data from Lee and Kim, we realized that in a vast majority of cases, this structure is actually an incredibly expensive, lossy workaround for a base model that is simply getting confused by the sheer volume of its own tools.
We identified the exact breakdown point, the disambiguation threshold around 80 tools. And we saw how treating an agent not as a magical persona, but as a localized namespace, is a vastly more grounded, structurally sound way to engineer.
We acknowledge the complex reality that sometimes multi-AG architectures are genuinely physically required to process heterogeneous hardware substrates, to enforce isolated safety boundaries, to coordinate in shared chaotic environments, and to execute massive parallel search vectors. But even in those necessary domains, forcing models to speak English to each other is a catastrophic bottleneck that the entire industry is currently racing to bypass.
And ultimately, we mapped the true life cycle of the swarm, not as a permanent static fixture of production architecture, but as a highly effective temporary training rig, a massive scaffold used to generate brilliant, complex reasoning trajectories that are destined to be internalized and absorbed into tomorrow's single foundational models.
Which brings me to a lingering, somewhat unsettling thought, something I really want you, the listener, to mull over and explore as we wrap up today. We've spent this entire deep dive methodically dismantling the corporate office structure of AI. We've proven, through rigorous research, that building multiple distinct agents is often just a temporary, inefficient training rig that is meant to be compressed into a single, highly capable entity. But take a moment and look around at what is happening in the human world right now. Across the globe, massive corporations are actively restructuring their human organizations. They are redesigning human workflows, eliminating traditional departments, and creating entirely new roles specifically to accommodate, manage, and mirror these sprawling multi-agent AI swarms.
We are radically altering human organizational behavior to match the current architecture of the machine.
Exactly. So here's the provocative reality to consider. If today's complex societies of mind are mathematically destined to be compressed into tomorrow's single, unified foundational models, What exactly happens to the millions of human organizational structures we are currently rebuilding to fit them? Are we permanently, irreversibly changing the nature of human workflow to accommodate an AI architecture that is, in reality, just a temporary set of training wheels?
That is a profoundly fascinating and admittedly terrifying dynamic to consider. We are conforming the human enterprise to the shape of the scaffolding right before the engineers tear the scaffolding down.
It has been an absolutely incredible, dense, and vital conversation today. Thank you so much for joining us on this deep dive, for pouring that coffee, and for dedicating the time to think through the real, grounded mechanics of our technological future with us. We will be back next time to unpack another massive paradigm shift, but until then, keep questioning the structures you see and keep looking for the math underneath the illusion.